Hi, this is Xiaochu at Lehigh University. For today's video, we are going to talk about the homework for week 11. Let's take a look at the first one. In example problem 6.9, water depths were required at critical diversion points located at upstream of the dam. Depths were only found at locations 188 meter and 423 meter upstream. We need to determine first the depths of flow at 748 meter and 1,675 meter using the standard step method and a spreadsheet program. Second, we also need to determine if the normal depths have been reached in the last cross-section. So based on the description of the problem and the spreadsheet, we can download it from the course site. So currently we have two kinds of data. The first one is we know the constant value of the constant parameters of channel and flow rate. Second, because the spreadsheet on the course site has already input the equations to calculate the water depth at 188 meter and 423 meter upstream. So what we should do is to complete this table to calculate the water depth at another two locations upstream. Let's first calculate the water depth at 748 meter. To do that, first we need to fill out the section number and delta L. Let's take a look at the figure on the left-hand side. Based on the different distance to the water dam, we divided the whole channel into different sections because we want to calculate the water depth at 748. So we need to set the downstream is at the section 3 and upstream is at the section 4. Then we need to calculate the delta L. Based on this figure, we know that the delta L can be calculated by using L3 minus L2. It equals to 325 meter. So next, we can copy and paste the equations of these parameters from section 3. Then we can get these values shown in green. Then we can input the equations to calculating the remaining parameters. For instance, to calculate the average slope of energy green line, we can take the average of these two values. And we put the asterisk here because it represents the values changes with water depth, which means that we input the equations here, but we did not explicitly to show the values here. Then based on the equation 12, we can calculate the head loss. And based on the equation 13, we can calculate the total energy at section 3. After we do that, we can calculate the parameters at section 4. Based on the equation 4, we can calculate the elevation. And based on the equation 5, we can calculate the cross-sectional area. Based on equation 6, we can calculate the velocity and the velocity head. Then we can calculate the latitude parameter and the hydraulic radius. Based on the equation 10, we can calculate the slope of energy grade line. And based on the equation 14, we can calculate the total energy at section 4. So currently, we already set up the equations to calculate the water depth at section 4. So what we should do right now is to try different values of the water depth until the total energy at downward, it equals to the total energy upward based on our energy conservation equation. So for instance, when we assume the water depth equals to 1.7 meter. Then we can read the number here. The total energy downstream, it doesn't equals to the total energy upstream. So we need to try another value. When we input the water depth, it equals to 1.74 meter. We could see that the total energy upstream, it equals to the total energy downstream. So we can make a conclusion that the water depth is 1.74 meter at 748 meter upstream of the dam. So based on the same procedure, we can determine the flow depth at 1,675 meter. And we can get the flow depth is 1.66 meter at section 5. So currently we know the water depth at section 5, it equals to 1.66 meter. And we can calculate the difference of water depth between section 5 and section 1. It's 0.34 meter. So we can make a conclusion that the normal depth appear to have been attained. However, it took a long distance upstream of the obstruction before this occurred, even though the dam only raised the water level 0.34 meter above the normal depth. Now let's move on to the second problem. In this problem, the water depth at different sections are all given. We need to use the direct step method to calculate the upstream distance, which is the value of L1 to L4. And then we need to answer how closely do this distance compare with the prescribed distance in the problem 1. So currently we have two kinds of information. The first one is a value of the constant parameters of channel and flow rate, which is represented in this table. And we also have the spreadsheet downloaded from the course site. And in this spreadsheet, we already input the given information, the water depth at different sections, into the third column. So what we should do next is to complete this table. Now let's calculate the L1 first. We should calculate these parameters based on the equation on the second slide. And then we can get these values, which is shown in green. And then based on this information, we can calculate the specific energy based on this equation, because in this equation, we already know the value of the water depth and the velocity head. Then we can calculate delta L based on this equation. And finally, we can get the distance to dam. For instance, the distance to dam at section 2, because L1 is the distance from section 2 to section 1. So the distance to dam at section 2, it equals to the distance to dam at section 1 plus delta L. So, which means it equals to 186 plus 0. So L1 should equals to 186 meter. After we repeating the same procedure to calculate L1, we can complete this table and get value of L2 to L4. And we can compare this value with what we have in problem 1. And we will know that the upstream distance that we calculated are very close to the distance pre-described in the problem 1. Now let's move on to the third problem. There is a 10-meter wide rectangular channel carries 16 cubic meter per second, and the value of roughness coefficient, slope, normal depth, and critical depth are all given. We also know that if a 5-meter high dam is placed across the channel, raising the water depth to 5.7 meter at location 5 meter upstream of the dam, we need to determine first the channel and flow classification, second, the water surface profile upstream from the control section. So in general, currently we have two information. The first one is a constant parameters of channel and flow rate, which is shown in this table. And second, because this problem asks us to calculate the water depth at a different section, we can directly revise the spreadsheet that we used in problem 1 to do that. Okay, let's do the classification first. Because we already know the normal depth and the critical depth. The normal depth is larger than the critical depth, so it is a mild slope. And after comparing the water depth with the normal depth and the critical depth, we know that the water depth is larger than this two. Therefore, the water level is at the section 1. So it belongs to M1 type. Then we can calculate the flow depth y. By following the same procedure in the first problem, we will get this table, but we need to pay attention because based on this problem, we need to revise two columns. The first one is a fifth column, because in this problem, it is a rectangular channel. Therefore, the cross-sectional area is equals to b times y, and the weighted perimeter is equals to 2y plus b. After we do the revision, we can try different values of the water depth at different sections to make the total energy at downstream equals to the total energy at upstream. Then we can get the water depth at different sections. Starting from this problem, the remaining problems are all about the culvert. So let's take a look at the problem 4. It asks us to determine the flow rate in a concrete culvert if the headwater is limited to a depth of 13.3 feet above the invert. The culvert has a squared edged entrance and is 50 feet long with a slope of 1%. We need to assume that the outlet is not submerged. For instance, we can assume that the flow satisfies with the category C. But once the flow rate is found, we need to verify that it is not category B by checking the normal depth. So first, let's calculate the flow rate. Based on the description of the problem, we can assume that the flow is in the category C. So based on this assumption, we can use the equation 8.19 to calculate the flow rate. In this equation, because it is a squared edged entrance, we can find the value of the coefficient of discharge. It equals to 0.6. And the area of the culvert is given. And we can calculate the head above the center of the pipe opening H by using the upstream water depth minus the half of the diameter. After we bring these values and equation into the equation 8.19, we can get the flow rate. It equals to 645 cubic feet per second. Then we need to verify our result. Because for the category B, the normal depth should larger than the barrel height. Then we need to calculate the normal depth. To calculate the normal depth, we need to calculate the value of this term and then use the plot on the right-hand side to determine the value of the normal depth. After bringing those values of these parameters back into this equation, we can get this term equals to 0.38. And then we can draw a vertical line, and this line intersects with the curve of the rectangular channel. And then we can read the value of yn over b, it equals to 0.8. Then we can get the value of the normal depth, it equals to 5.2 feet. Because this value is smaller than the barrel height, which is 6.5 feet. So we can know that this flow situation, this scenario, it belongs to category C rather than the category B. Now let's take a look at the fifth problem. The city engineer is concerned about damage to homes upstream of a box culvert during the 100-year flood event. The concrete culvert with a square-edged entrance condition is 15 meters long and has a bottom slope of 2%. Backwater computations show that the tailwater depth is 2.75 meters above the invert of the box culvert during this flood event. An upstream water depth of 3 meters will begin to flood homes. We need to determine are the homes in danger of flooding, and we also need to calculate the velocity of flow through the culvert. To determine are the homes in danger of flooding, in other words, we need to calculate y sub u and compare it with the maximum y sub u that prevent flooding, which is 3 meters. So it means that if y sub u is larger than 3 meters, then the home will be flooded. To do that, first we need to determine which category this scenario belongs to. Because we know the diameter is lower than the tailwater elevation. Therefore, the outlet is submerged. So this scenario, it belongs to category A. And based on the equation provided for the category A, we can calculate the head loss. Because it is a square-edged entrance, we know the coefficient. It equals to 0.5. And because it is a concrete culvert, so n it equals to 0.0310. And we know the length of the culvert is 15 meters. And we can calculate the hydraulic radius by using the area divided by the wetted perimeter. Because the culvert has already submerged in both inlet and outlet. Therefore, in this situation, the wetted perimeter should equals to the perimeter because it is a rectangular channel. So it equals to 2 times 4. Therefore, we can get the hydraulic radius. It equals to 0.5 meters. And we also know the flow rate for 100-year flooding events is 12.5 cubic meters per second. Then we can get the value of the head loss. It equals to 0.81 meters. If we write the energy equation at the entrance and exit, we know that the headwater elevation it equals to the tailwater depth plus the head loss. the headwater elevation is equals to the water depth plus the elevation. We can calculate the elevation by using the slope times the culvert length. In this equation, we already know the slope length, tilt water depth, and the head loss. Therefore, after we bring the value to these parameters, we can get the upstream water depth is equals to 3.26 meter. And then we can compare it with the maximum upstream water depth. It is higher than that value. Then we know that the homes are in danger during the 100-year flood. And because the velocity equals to Q over A, then we can calculate the velocity is equals to 3.13 meter per second. Now let's take a look at the last problem. In this problem, we need to determine the size of a circular corrugated metal culvert that will fulfill these design conditions. For instance, it should be a 200 feet length, a 0.1 slope, and a flow of 88.2 cubic feet per second. The outlet will be unsubmerged, but the inlet will be submerged with a head water depth of 6.6 feet above the culvert inlet. Based on the design conditions, the culvert satisfies with two categories, the category B and category C. Let's assume that the culvert is in category B first. So based on the energy equation, the head water elevation is equals to the tail water elevation plus the head loss. The head water elevation is equals to the water depth plus the water elevation. The tail water elevation is equals to the diameter. So in this equation, we know the value of the upstream water depth, the slope, and the length of the culvert. Then we can know that the head loss is equals to 26.6 minus the diameter. We call it the equation 1. And because in this situation, the culvert is in category B, so for the full pipe flow, according to the equation 8.18, we can calculate the head loss by applying this equation. Because it is a squared edge entrance, the coefficient equals to 0.5, and it is a corrugated metal, so the N is close to 0.024. The length of the culvert is 200 feet. And because it is a circular culvert, then the hydraulic radius should equals to d over 4. And we also know the flow rate. It equals to 88.2 cubic feet per second. Then we can use this equation to calculate the head loss. And because the both equation 1 and 2 are represent the head loss, so the equation 1 should equals to equation 2. Then we can get the value of the diameter. It equals to 2.75 feet. After that, we can assume that the culvert is consistent with the category C. Because for the category C is partially full flow. Then based on the equations 8.19, we can calculate the flow rate. And because in this equation, the flow rate is given, it equals to 88.2 cubic feet per second. And because it's a squared edge entrance, the coefficient is 0.6. And we can calculate the cross-sectional area by using pi times d squared divided by 4. And the height above the center of the pipe opening, it equals to the upstream water depth minus the diameter divided by 2. After we bring these values of parameters and the equations back into equation 8.19, we can calculate the diameter. It equals to 3.25 feet when it in category C. Because in practice, we typically choose a larger diameter for design. Therefore, the culvert will operate under the flow classification C, and the required diameter should equals to 3.25 feet.